Okay, so in this video we're going to solve problem F1-15 in Hibbeler. So what this one is, this is a pretty classic type of problem, so it's good to get used to these. Bolts very often are behaving in shear. That's the fundamental way that they fail. So here are 3 plates, and they're held together by 2 bolts going through. The loads of the plates are shown here. So this is actually what's called a double shear problem. It's because you have 2 shear surface areas. One between this top plate and the middle plate, and another shear line between the bottom plate and the middle plate. So actually these bolts are what act as double shear because there's 2 lines of shear going through them. Okay? But anyway, fine. So the problem here is they give you the forces on the plates and they want you to determine the maximum average shear stress in each of the bolts, and it tells you that each bolt has a 3/4 inch diameter. So we can get the cross-section area. All right. Let me just tuck this up here for now. Keep that up in the corner so at least you can see the picture. Okay, so with this problem, again, we need to get the maximum shear stress, and this is the shear force. I should say the maximum average shear stress. It's the shear force acting over the shear area. Okay? And so the question is, what is the shear force on each bolt, and what's the appropriate area? Okay. What's the best way to draw this? Well, if we look at the loadings on the plate, everything's kind of symmetric, so I'll make one assumption that each bolt is going to carry the same amount of load, okay? So if you look at it, there is no asymmetry that would say this bolt carries less force than this bolt. So in the sense, we can assume them each carrying half of this 5 pounds on each plate on this side and 10 on this side. All right. So first of all, you also notice that obviously the 2 5 pounds balance the 10 pounds, and this is again an equilibrium problem. So one way we can kind of draw this is if I draw the bolt. We'll draw one of the bolts. Here's the head of the bolt, and here's the threaded part of the bolt. And basically, if we look at a cross section, I'm looking right through one of these bolts. Right. Here's that top plate with the 5 kips. But I'm going to cut it in half because this is one bolt. So I'm going to do it as... well, there's 2 ways you can do it. Well, let's do it. Let's keep it at the 5 kips. And I'll argue it a different way. And then here's the bottom plate. Also with the 5 kips. And then here's the middle plate. For some reason I can't draw hatches in this direction as nicely. And then here's the 10 kips that my hand's blocking. Okay, but there you go. So in this case, we can think of the 2 areas of shear going on here, right? So let's look at the shear going across that surface, all right? So let's cut the bolt. And we have 5 kips acting on the bolt above. So this is, again, I guess I should draw the arrow this way. So this is actually along that shear line. And then down here, we have the internal shear force, right? Call it V. All right. You can do sum of forces in the x direction, and you can see that V has to equal the 5 kips. Okay. You can do the same down here. You know, we can draw down here. You get a similar picture. If this is the bolt, the bottom end of the bolt. Here's the 5 kips applied from that plate, and that would mean that you would have a V on this surface of 5 kips. Okay? So 2 different sections. So these are actually 2 different points in the bolt. Okay? So generally you need to check both. Okay? But you can probably see here we got the same V in the same area, so you'll actually will get the same stress either way. All right. So that's the stress. Now what's the area? Well, the area in this case is the area of both of these bolts added together. Why both? Because this is the total force carried by is carried by both of these bolts. So it's the cross-sectional area of each one of these added together. All right. You know, originally what I was saying was I would cut the force in half, but this is probably a little more correct, I guess, way of discussing it. All right. So the area is actually 2 times pi times the diameter, which was 3/4 of an inch squared, and then we have to divide by 4 because we're using the diameter, and the V is, in both cases, 5,000 pounds. All right, so let's compute this. I can never find my calculator. Let's compute the V, the area. So the area is 2, 3, 4, 5, 6 times 4 divided 3, 4 times. Okay, I'm getting the area to be 0.8835 inches squared. So that's the cross-sectional area again of both bolts. That's the 2 bolts. So this is okay. This is the area in which the shear force acts on. Right. So another way you can look at it. If you look down from the bottom view, here are the 2 bolts. Here's their cross-sectional area, and you have the shear force, the V, acting on both of those, right? Well, I should say the V. The V, in a sense, acting on this total area. Okay? So it's the V of the 5 kips over that total area. All right, so it gives me the tau is equal to 5,000 pounds over 0.883 inches squared, and that gives us 5,658 psi. And so that's the answer. Okay? So again, this is a very simple problem. You get a shear stress on this one of 5.6 kilopascal, and same here. Okay, so if we were to look, just to take this one step further, while I got you, this is again, this isn't necessary for the problem, but this is just a comment to help get used to the visualization of the stress and the component. So let me try to draw the bolt again. Let me draw it here. This is the whole bolt. And so basically we have the five kips, the 10 kips, and then the 5 kips. Okay? So don't be confused and do the 10 kips over the cross-sectional area, right? That's not the shear force. You have to get the shear force by looking at the cross-section. So if we take a cross-section here, and look at a little element of material here, right? From the top side, look, if we're looking at this, the top half of the bolt, right? There would be a shear force acting in this direction on that little chunk of material. And this is the 5,000 pounds. Now you divide that by the cross-sectional area that it works on, this will give you the 5,658. Oops, 5,658 psi. Okay, in that direction. Now if we looked at the other joint on the bottom, and looked at the little chunk of material here, it's another shear situation. In this case, this one will force reacting that way. So if I kind of split these out, just to show it. Right? 5 kip that way, 5 kip that way. And if we draw the middle section, 10 kip in the opposite direction, 5 kip. Equal and opposite direction because that's the section. 5 kip here. And then the bottom part of the bolt, right? 5 kilopascals. And then here's the shear force, 5 kilopascals. So that's the way the bolt is going to see the shear. So it's going to kind of do something like this. I'm kind of exaggerating the deformation of the bolt. If you want to think of it, it's shearing on those surfaces. Okay? All right. Well, I hope that was helpful. It's a simple problem. Get used to it because this concept of figuring out the shear forces in bolts are going to be done many times throughout your career. And it's a little twist because of the area. And also it gives us a good idea about trying to visualize that shear state of stress. Okay, thanks.